My name is Ashley Swansea, and I am going to be pursuing a career in radiology or sonography. And this is my presentation on Hooke's Law.
My name is Colby Swansea. I'm majoring in instrumentation, and this is my presentation over Hooke's Law.
My name is Jackson Whittington. I am majoring in instrumentation, and this is my project over Hooke's Law.
So our project is on Hooke's Law. My name is Allie Dehart. I am in a group with Ashley, Colby, and Jackson.
So, Hooke's Law describes how elastic materials stretch and compress, such as a spring. One of the key definitions related to Hooke's Law is spring constant, which is a constant that is often symbolized as K, and it's going to tell you how stretchy or stubborn a spring is. Hooke's Law was discovered by Robert Hooke in 1660.
Okay, this is my introduction to Hooke's Law. Hooke's Law helps in designing structures that can withstand forces without permanent deformation. One of the key definitions for Hooke's Law is strain. Strain is the relative deformation produced by stress, expressed as a ratio of the change in the length of volume to the original dimensions. The behavior of elastic materials under the application of force is crucial for understanding everything from the springs in your mattress to the suspension in your car.
My name is Jackson Whittington. This is my introduction slide over Hooke's Law. Materials often resist deformation when a force is applied. Think of something almost like a spring or rubber band. If you take and stretch that spring or rubber band out a good amount and let it go, it's going to return back to its normal state. The relationship between the force and resulting deformation is key to understanding material behavior, which is shown here in the formula F equals K of X, in which F is your force being measured, K is your spring constant, and X is your deformation, otherwise known as stretch or compression. Hooke's Law provides a mathematical model for predicting how objects such as springs behave, also shown in your F equals K of X formula.
Introduction. Most things can be stretched. It may also have to be heated, but it can be done. When skin is stretched in infants, they can be stretched 75% before it tears. The elderly can be stretched 60%.
One of the specific fields that applies Hooke's Law is biomedical engineering. They're focused on designing medical devices, prosthetics, imaging systems, and biomaterials. This aims to improve healthcare, of course, diagnostics, and patient outcomes. One of the examples that I provided is cardiovascular devices such as stents and heart valves. They're designed to help flex and return to shape. The stents in compliant vessels rely on elastic deformation. So Hooke's Law will help to ensure that they flex properly without any permanent damage. Another example that I provided is prosthetics design. This is artificial limbs that will mimic muscles and tendons. Engineers use Hooke's Law to model how these components will respond to movement.
The second slides will be over the related fields. The specific fields are structural analysis. It's critical for ensuring safety and performance. The examples are the Taj Mahal is a prime example of structural analysis. It showcases the use of structural design principles to create a monument that can withstand various environmental conditions. The second example is offshore platforms. Offshore platforms are designed to endure the forces from waves, wind, and seismic activity. These structures require careful structural analysis to ensure they can withstand the dynamic forces they encounter.
As far as related fields go, mechanical engineering, anyone that does some sort of mechanical engineering uses this nearly every day. As far as Hooke's Law goes, it's more or less used to design spring suspension systems, anything like load-bearing components. Think of something like the suspension in your car. It uses things like shocks, springs, dampers, whatever. Basically to give you a smooth ride over bumps, rocks, curbs, anything that might be in the way on the road. It's also used when building bridges and buildings to more or less help with how these bridges and buildings flex, say through the wind or through traffic. Really overall just following the elastic behavior principles.
Related fields. Specified field is skin. Skin elasticity is needed because when you cut yourself and need your wound to heal faster, your skin can almost reconnect itself. Applies because skin can be stretched to a limit. Example, when I broke my hand, I split open my palm, but they put stitches in my hand to get my open palm to stretch out and make the skin close the split open palm.
One of the scientists that is related to Hooke's law is Robert Hooke. He was born July 18, 1635, in Freshwater, Isle of Wight, England. He died at 67 on March 3, 1703, in London, England. He studied at Christ Church, Oxford, in England, but before that, he attended Westminster School in London. Robert Hooke is famous for many things, but just to state a few of them, the one we're talking about today, his discovery of Hooke's law. Again, it was discovered in 1660, however, it was first published in 1678. He was also famous for observing and naming cells. He became the first to make this observation and come up with the term after he examined a slice of cork under his microscope. He did research many things, but one was pendulum springs and balance mechanisms that were used for timekeeping. This research helped him to revolutionize timekeeping by inventing the balance spring, earning him recognition as a pioneer in precision mechanics.
A relevant scientist of Hooke's law is Isaac Newton. Isaac Newton was born January 4, 1643, at Woolsthorpe Manor in Woolsthorpe by Costleworth. He died on March 31st, 1927, in Kensington. He attended King's School in Grantham, showing early interest in mechanics and building modules. He's famous for laws of motion and the universal law of gravitation. His research topics are motion, calculus, and telescopes.
My relevant scientist, I chose Augustin Louis Cauchy, who was born on August 21st, 1789 in Paris, France, and later died on May 23rd, 1857 in Sceaux, France. He studied at École Polytechnique from 1805 to 1807. Now, Cauchy, he really expanded on Hooke's law. He used more three-dimensional structures or buildings or whatever, and also more complex materials. He developed the mathematical theory of stress and strain. Basically, if you stretch or bend or anything, how long it's going to take to get in. He also introduced the Cauchy stress tensor, which is used in engineering and physics to predict material behavior, basically predicting how a cable is going to act under so much stress, or how a spring is going to act over so much stress. Without him, we wouldn't be able to test the internal stress of things like buildings or cables or bridges, things like that. He really contributed to calculus, elasticity, and fluid mechanics throughout all of these discoveries.
Relative scientist. Thomas Young was born June 13th, 1773, in Milverton, Somerset, England. Died May 10th, 1829, in London. Studied in London in 1801. Famous for naming astigmatism and the study of light. His most important role was finding out about light and everything there was to know about it.